everybody. We're going to talk about rational functions, um, and we're going to talk about graphing and finding all the different identifying features of a rational function. Sorry for my voice, I'm kind of under the weather, but we continue and soldier on. Now, the first thing that you want to do, and we'll go out this way with this, is you want to find discontinuities. And these discontinuities I've described in other sorry about that, I'm focusing things in here. Discontinuities are going to be points where within the domain of the rational function, the function doesn't exist. So these are points that we are going to excuse from the domain. I call them problem children, and I kick them out of the domain. But these discontinuities are going to be very, 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 very difficult. Well, they're not very difficult to find, but you need to be able to discern the difference between these different types of discontinuities. Once you find discontinuities, and usually what you're going to do is you're going to set the numerator equal to 0, and every x value that's going to make the numerator equal to 0 is going to be a discontinuity. Now they fall into two categories: the vertical asymptote, which I just read on a website. I was doing some research on the difference between vertical asymptotes, horizontal asymptotes, and what I call oblique asymptotes, but some people call slant asymptotes. Vertical asymptotes are sacred. You put these in, they are vertical lines. Your graph cannot cross these. They cannot touch these. They are poisoned areas of the graph where you cannot touch them. Or you get holes. Now, for example, if you have f of x is equal to x over x plus 1, you're going to have a discontinuity at x plus 1 equal to 0, which means x equals negative 1. Now, if we look at this, there's nothing to divide out. There's nothing we can do. The x minus 1 is the only point that's going to make this thing undefined. We're actually going to get a vertical asymptote. At x equals negative 1, so we'd end up drawing a dotted or a dashed line at x equals negative 1. Now with holes, it's a totally different story. Say after you factor everything, you get x plus 3 and x minus 1, and in the bottom you have x plus 3 and x plus 4. Now, you have discontinuities. At x equals negative 3 and x equals negative 4, because that would make both of these factors equal to 0. But the problem is, and this is the main difference between an asymptote and a hole, is when you have factors that can divide out, as we do with this, this is going to be a hole in the graph. Yes, it is a discontinuity because we are graphing the original function and not a different function. But if you divide those two out, you get x minus 1 over x plus 4, which is going to help you if you have to find points, things like that. This graph is going to be identical to this graph, except for this graph is going to fill in the hole. But we have to account for the original, not something that we've algebraically manipulated. This isn't the graph of f of x. This is just a helpful tool for us to find points that we need. Now, since x equals -4 or x plus 4 here cannot be divided out, we can say that this is going to be a vertical asymptote. So the first thing you do is you find your discontinuities and you go from there. Now the next thing you want to do, find your zeros. This is where the numerator is equal to 0. So if you have f of x is equal to x over x plus 1, you have a 0 at x equals 0. Just take the numerator, set it equal to 0, you're good to go. If it gets more complex, like for example in this one, we're going to have a 0 here. Because this is already tied up in the hole, that's not going to cross the x-axis anywhere. It's going to cross the x-axis here at 1. And we can kind of tell that from over here too. So all you do is you set your numerator equal to 0 and solve from there. So if you have f of x is equal to x plus 1, x minus 2, all over x plus 3, x plus 4. I know I'm going to get zeros at x plus 1 equals 0, which is x equals -1. I'm going to get zeros also at x minus 2 is equal to 0, so x is going to be equal to 2. So I know from here that -1, 0 is on the graph, and I know here that 2, 0 is on the graph, which is nice to know. Another thing that we can find out, horizontal asymptotes. Now, horizontal asymptotes aren't nearly as sacred in the world of mathematics as the vertical asymptote. The vertical asymptote, like I said, it's a sacred thing. You can't touch it, you can't go through it, you can't do anything. It's there, and it cordons off anything. It's a force field, essentially, inside the graph. The horizontal asymptote is kind of like a suggestion, but it also kind of tells us things about end behavior of these graphs. What are the end behavior going to do for the different branches of our graphs? Now, the horizontal asymptotes, if you have y is equal to a over x minus h plus k, the horizontal asymptote is at y equal k. Yeah, that's nice. If you have y is equal to ax plus b over cx plus d, your horizontal asymptote is at y is equal to a over c, which is nice. If you have y is equal to ax to the n power plus dot 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 over cx to the n power plus dot 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 dot, and these two values are the same, you're going to get y is equal to a over c again. If you have y is equal to ax to the n power over cx to the m power, and m is greater than n, your asymptote be y equals 0. And if y equals ax to the n over cx to the m, and n is greater than m, you could get a slant asymptote. which is something we won't do a whole lot with. Uh, so we're going to keep the realm of these different ideas as we kind of go through everything. So these are some of the big things that we want to be able to do. And then once we're able to find discontinuities, which is big because remember we have these branches that are going to branch out. You get your zeros, you get your horizontal asymptotes. Uh, now I guess we could say to you, what are you responsible for? What do you need to be able to find? Discontinuities. Vertical asymptotes. Holes. Horizontal asymptotes. And like I said, we're going to keep things simple as far as that stuff goes. And zeros. Then as far as the graph goes, you're going to use your calculator, the Inspire, and then sketch the graph. But I want you to have a nice understanding on the discontinuities. Where does the function not exist? So if I go out a little bit, I know that's not the best picture, but those are some of the good ideas that we're going to be dealing with. Now, what I'm going to do is I'm going to jump over. Got to find the question. And here we go. This was one of the homework problems. And when you deal with this type of situation, let's make it all nice and pretty. First thing you do is you factor. So we're going to get y is equal to x plus 3, x minus 2, because I need two numbers that multiply to get to negative 6, that add to 1. That's 3 times negative 2, works out. Now, for negative 4, x squared minus 16x minus 12, I'm going to take out a negative 4 because 4 goes into 16 and 12 and 4. And the negative sign makes everything positive, which makes factoring the quadratic part easier. So I'll get x squared plus 4x plus 3. And that's going to be equal to negative 4 times x plus 3. Because I need two numbers to multiply to 3. That's only 3 and 1. That add to 4, 3, and x plus 1. So I get negative 4 times x plus 3, x plus 1. Now 2, I got my discontinuities. I hope I spelled that right. That's an N right there. Alright, now I look at the denominator. What number makes this 0? X plus 3 equals 0, x equals negative 3. Then I have x plus 1 equals 0, x equals negative 1. Now, the question is, not hole or vertical asymptote. Now, if you could divide any of them out, I could divide these two out right here. So if I could divide them out, this one means that's a hole. And that's VA, the vertical asymptote. Alright, so I was able to find that. Now, part 3, my zeros. This part here is already taken up because it's part of a hole. I don't know if that's going to hit the x-axis or not. We'll see. But I know x minus 2 equals 0 is a hole, is a 0. So x is equal to 2. My horizontal asymptote since I have x squared and x squared, same power, I just take the lead coefficient here. So y is going to be equal to 1 because there's a 1 right there and 1 over negative 4. So I'm going to have those. Now, in this case, I'm able to figure out my discontinuities. I have my hole, I have my vertical asymptote, got my zeros, got my horizontal asymptote. I think we're ready to go. Now, the next thing that we want to do is we want to get into the graphing calculator. And here's the graphing calculator. And I want to type in the original equation, so I need a rational situation. So I make a fraction. I'll get x squared plus x minus 6. You get negative 4x squared minus 6x minus 12. Hit enter, and here we go. I hit tab, and I want negative 1, well, no, tab. Alright, negative 1 over 4 and always fun. Alright, get rid of that. You can see the horizontal. I can open it up and say I'll go negative 1, enter negative 9, and then I'll say wherever you see undefined at negative 3, x equals negative 3, there should be a hole right there. That's your hole. X equals negative 1 is undefined as well. There's your hole. There. This is your vertical asymptote. That's your hole. And then you can